Section 5.2 is about compound interest. And usually if it's larger amounts over longer time periods, it's more common for interest to be compounded. You're paying interest on your interest, or you're gaining or earning interest on your interest as well as on the principal. So we still call the beginning amount borrowed or deposited the principal. And in your book, they use PV as abbreviation for present value. And interest rates are still usually quoted as a percentage per year. You need to convert it into a decimal to use it in any interest calculations. And then we have this I, that's the interest rate per period. So when you're compounding, you get quoted an interest rate per period. And it's the interest rate R divided by the number of periods per year. So if you're semi-annually, then I is R over 2. If you're quarterly, I is R over 4. And you can see that monthly would then be R over 12. So then we have N, which is the number of compounding periods total. So let's do an example of this where, let me keep the formula where you can see it. So the future value of $15,000, where we're now compounding, so we have 1 plus, the interest rate is 4.6%, and it's compounded annually. So then I equals R. So we need the R as a decimal though, 0.046. Then the number of compounding periods is 11 each year, once per year. So 11 times total, it will be compounded. And so we're going to get 24,627 cents. So that's the compound amount. And then if we want to know how much of that is interest, we would subtract off the present value that we started with and get $9,600.27. So 2 answers. Make sure you're watching for that. We can also solve for the interest rate needed to accomplish a particular goal. So let's see how that would work. Find the interest rate to end up with $39.05 when you started with $25.50. You're going to have 1 plus, then your interest rate of R, compounded 11 times. This is an exponential equation. So we want to get the exponential part isolated. So we're going to divide both sides by 2550. So then we'll have 3905 divided by 2550 equals 1 plus R to the power of 11. Well, to undo to the power of 11, you take the 11th root, or you can take 3905 divided by 2550 to the power of 1 over 11, remembering that those are equivalent. The 11th root and 2 the power of 1 over 11 are the same. So that's going to give me an R about 1.0395. Sorry, the 1 plus R is going to be 1.0395. So then subtract 1 from both sides and get R is about 0.0395. And then we have to convert that to a percent. So we'd get 3.95%. You'd need to have at least that rate for your 2550 to grow to 3905 in 11 years. So here's some common compounding periods: semi-annually, quarterly, monthly, and daily. So make sure to make a note about semi-annually. Sometimes people get that confused with biannually, and that's every other year. So every 2 years. Whereas semi-annual means twice in each year. So in those cases, you have to divide your interest rate by the number of times you compound in a period. So let's look at this example where we have the future value of $6,700. I'm going to have 1 plus my interest of 0.046. I'm compounding quarterly. So 4 times a year for 8 years. So that means 32 times the compounding will happen. And you'll end up with 966013. And then we're also asked to find the interest. So the interest will be the 966013 minus the 6700 we started with, or 296013. And I'm thinking I forgot to, oh no, I did it in that previous one. Okay, so there's a limit to this compounding business where if you compound it more and more often, so we looked at semi-annually, then quarterly, then monthly, then daily, then every hour, every minute, every second, the limit is if you compound continuously. So it turns out there is a limit, and it is E. That's if you compound continuously. So the only time you're going to use this formula is if you see the word continuously. Otherwise, it's periodically, and look for one of these words that tell you how often it's being compounded. So let's look at what our future value will be if we put 100,000 in and have E, and the interest rate of 0.053 written as a decimal for 22 years, and make sure that's all up in the exponent. And you'll end up with 320,913.04. And then we're asked to figure out and the interest. So that's going to be the 329,13.04 minus the 100,000, or 229,13.04. That's a boatload of interest. Okay, so let's talk about another business application that comes up that you may not have run into in your experience, but I remember talking about these in second semester accounting, these zero coupon bonds. And there used to actually be paper and little coupons on them that you'd tear off and bring somewhere and get money for it. So they don't do that anymore, but the name of the vehicle has persisted. So zero coupon bonds, you don't make any interest payments during the life of the bond, and the person holding the bond just gets a single payment at maturity. The interest is compounded semi-annually. It just isn't returned until the end of the term. So the bond is sold at a discount from its face value. So the difference between the face value and the price paid will be the amount of interest earned. So if the price is $13,328 and I have an interest rate of 4.1%, so that's 0.041 as a decimal, over semi-annually. So semi-annually is part of the zero coupon bond. As soon as they say it's a zero coupon bond, then you know it's semi-annually. And we're just going to say it's twice per year for 10 years, or you could just figure that out and write the 20 there. And that's going to be, you could either call it the future value or the face value. Those have the same meaning in this particular scenario. And then this says round to the nearest dollar. So it comes out, if you round it to the nearest dollar, to 20,000. So the face value is 20,000. You would pay $13,328, and then 10 years later you would get 20,000. Okay, then this is a really helpful idea, this effective rate. So this is a way to compare different kinds of investments or different kind of loans to come up with an effective rate so that you're comparing them on the same basis. So I like to think of it as investing $100 and see how much you'd end up with, because it makes it really easy to see what the percentage is. So if you put $100 into an account and it had a rate of 8% compounded quarterly, after 1 year, you'd have 108. So you earned $8.24 on 100. Well, that's the same thing as percent. So it's an 8.24% is the effective rate of 8% compounded quarterly. So it's also called APY, or annual percentage yield. And typically R is used for the quoted rate or the nominal rate. So I thought it might be helpful to put all of that in one place here. So 8% is the nominal rate, or it's also called the stated rate. Then 8.24% was the effective rate, because when you compound it, they effectively get more money from you. Or it's also called the annual percentage yield. So it kind of depends on if you're paying out money, you would probably call it the effective rate. If you're getting money from an investment, you would say the investment yields 8.24%. So this symbol, lowercase r, subscript capital E, is also commonly used for this effective rate. So let's find the APY corresponding to a nominal rate of 6% compounded quarterly. So I'm going to do it how I said I would. So I'm going to do 100 plus my rate of 0.06% over 4, because it's getting compounded quarterly. Then I would compound it 4 times for 1 year to see how much I end up with at the end of that 1 year. So I end up with 106.136. So I can see that I gained $6.136 on $100. So that is percent. So that's the same thing as 6.136%, lowercase r, subscript capital E. So if you want a formula, here's the formula. This is done as if you put $1 in, and then you subtract off your original dollar. Then you have to convert it into percent. So I like my way better, where I work with $100, then my answer comes out already in percent. But it's totally up to you. So suppose you know interest is going to be compounded, but you want to figure out how much do I put in now in order to have a certain amount. So the future value is what you know. I want to have, say, $35,000 to buy a car 5 years from now. How much do I need to put in now? So there's 4 different variables in this formula: future value, present value, interest, and number of periods, or how long are you going to put the money in for. If you know any 3 of them, you can solve for the 4th one. So this formula is really the same formula that we've just been using for interest computations. Just if you divide both sides by 1 plus I to the n and solve it for the present value, then it looks like this formula. So one way to think about the zero coupon bond is that its face value is a future amount, and figure out what the present value is to decide whether the sale price is reasonable. So let's look at how this would work out. I want to end up with $10,000. So I want to know what the present value should be. I'm getting 4% interest semi-annually, because this word zero coupon bonds needs to prompt you semi-annually. I'm just reminding you. And then it's 2 times each year for 10 years. So then see how you would divide both sides by this exponential part. I simplified it a little bit to figure out what would the selling price be, 67.29.71, that if the selling price is that much or less, I should jump on this because I'm going to get $10,000 at the end, and that's a reasonable amount. So present value is also a useful way to think about inflation. So if you think about the past as the present value and now as the future value, then if we think about an item that costs $1,250 now, I would divide by the 1 plus 0.0118, and we assume inflation is annually, and then it would be 6 years. And we say, well, what then would be the value in the past? And we'd say it would have been $1,165.04 to buy that thing 6 years ago. And today it will cost $1,250 to buy it. So that's all there is to section 5.2. Enjoy the homework.